Okay, so okay, so can you hear me?
Yes.
Okay, sure. So let's start our lecture today. Today again it is going to be lightweight because so the two algorithms that we're going to introduce are based on depth first search, and it is an optional algorithm. So which means that these two topological sort and strongly connected components, they are also kind of like optional. We just need to know the existence of these two algorithms and what is the what kind of things or what kind of problems can they solve. That's what I want you to learn. So you don't have to implement them. Okay. Let's go through what we learned last week. Last week we learned the graph data structure and the two different representations of that, which are the adjacency list and adjacency matrix. And then we learned two search algorithms for the graph. The first one is called breadth first search, and then the second one is called depth first search. So we put more focus on breadth first search because it is more definitely more important, way more important than depth first search, because if you check the output so of depth first search, it basically it takes that this input is a source node, and then it is its output is the minimum distance from so for every node in the graph, it is going to give you a d. Where d denotes the minimum distance from the source to this node. So that's why it is so important, because the output conveys is very meaningful. And so then we learned the depth first search algorithm. So which is relatively not that important. So I didn't go through the details of that too much. But the thing that I expect you to learn is that for the output of depth first search is that for each node, it is going to associate it with a two values, which are u.d and u.f. So what does d and f mean? What are the meanings of d and f? D means the discovery time, and F means the farewell time. Farewell time, or say the finish time. So it is the time that we're going to say goodbye to this node. Okay, so but these two different times, they don't deliver special meanings. But as I said last time, so we are going to use them for some of other algorithms, which are the two algorithms that we're going to learn today: the topological sort algorithm and also the strongly connected component algorithm. So this is the a picture that shows the difference between depth first search and breadth first search. On the right hand side, we have the breadth first search. So from the source node, we first visit the nodes that are whose distance to the source is 1, and then we're going to visit the nodes whose distance to the source node is 2, and then we're going to visit the nodes whose distance to the source node is 3. So it's like we gradually increase the search radius. Whereas the depth first search is this. So the first time when we pick the from starting from the source node, we just pick one direction, and then we go to the very end of that direction, and then come back to the source. Next time we are going to pick another direction, say this direction, and then we're going to go to the very end of this direction. So basically, in this way, we visit each node twice, on the way going forward and on the way coming back to the source node. So the first time when we go through the node, we say it's the discovery time. That is the discovery time. And the second time that we're going to visit the node is the time that we're going to say goodbye to this node. So we call it finish time. So that's the output of depth first search. And this is what the explanation of that. So D is the time that we turn the color from that node, turn the color of that node from white to gray, meaning that the first time we discover it, and then F means that the time that we're going to say goodbye to it, meaning that we're not going to visit this node anymore. So we're going to change its color from gray to black. Okay, so this is the brief overview of the two algorithms that we learned last week. And today, the first algorithm that we're going to learn is this called topological sort algorithm. So the input is that we're going to give a directed graph. So this graph comes with the edges of this of the input graph come with the directions. And what we want to do is that we want to get a linear ordering of all the nodes in the graph, such that if there is an edge in the graph, if there is an edge from U to V, and then we want to make sure that in the total ordering of the vertices, U appear before V. Okay, so if there is an edge, so if there is an edge from U to V in the graph, and then in the total ordering, we want U to appear before V. So that's the requirement. Okay, so and here you may be so confused of why do we want to have this? Why do we want this output? Why do we want the output to be like this? And here is one example. Okay, so so this is an input graph which is directed, and so the vertices are just different pieces of clothes that we need to wear in the morning. So for example, we got undershorts, pants, belt, and shirt, tie, and jacket, socks, shoes, and watch. So here you can see that we have an edge from undershorts to pants. The reason is because if there is an edge from undershorts to pants, it means that we need to put on undershorts before pants. And then there is an edge starting from pants to belt. Then this means that we should wear pants before wearing belts. Similarly, we have an edge starting from shirt to tie, and this means that we need to wear shirt before wearing tie. So here you can see that the edges definitely represent something. So it represents, okay, which piece of clothes should be worn before which piece of clothes. And this is the meaning of the edges in the graph. So basically, if there is an edge from U to V, and then it means that U should be before V. Okay, and then so the output. So if we apply this the topological sort algorithm over this input graph, we basically want to have an order. Sorry, we basically want to have an order of all the nodes inside the graph, such that undershorts appear before pants, undershorts appear before shoes, pants appear before shoes. So basically, it tells us, okay, by following which order should you wear your clothes, and then in that way you will be trouble-free. Okay, and then so let me say, okay, before I introduce this algorithm, the detailed algorithm, do you have any question regarding the definition of the problem? What is the output of the algorithm?
In terms of the numbers or the letters?
No. So for now, you should ignore the numbers. You don't need to look at the numbers. Just understand why do we want to. So here, just trying to understand what is the output of the algorithm. The input is basically a directed graph like this, and then the output is an ordering, or it's basically an order of the nodes, such that if there is an edge from U to V in the graph, then in the total ordering, U should come before V. Okay, so for now, you don't need to look at these numbers, just look at the nodes. The example is that we have different pieces of clauses. And so here, and we build a graph. We build a graph where the nodes are different pieces of our clauses, and then the edges represent which should be where before what. So for example, we should where, here we have an edge from undershores to panes, and it means that we should wear under panes before, we should wear undershores before panes. Similarly, we have an edge from undershores to shoes, and then it means that we should wear undershores before shoes. So if we apply topological sort over this input graph, the output is basically an ordering of these nodes such that it guarantees that if we follow that ordering to wear different to wear different pieces of the clauses, then we will be trouble-free. We will not get into a situation where we put on our pins first, then we just realize that we haven't put on our undershores yet. Okay. So this is the definition of the problem. The output is basically an ordering of the nodes such that the ordering respects the edges in the graph. And here is the algorithm. Okay, so this is the algorithm to the topological sort algorithm, where we have an input with graph G. And so what we do is that first we call the depth first search over the graph to compute the finish time of every node in the graph. Okay, so here, let's say these numbers here, these numbers represent, the left number represents the discovery time, and the right number represents the finish time after we apply depth first search over this graph. Okay, so here we can say that the finish time of undershores is 16, and then the finish time of panes is 15. The finish time of belt is 7. Okay, so first it asks us to compute the finish time for each node, and so these are the finish time of the nodes. And then what it says is that as each vertex is finished, we insert it into the front of a linked list. So the way that we build the linked list is this. So what is the node that we finish first? Which node is finished first? Or which node has the smallest finish time?
The jacket, I think. The jacket.
No, I think it's the jacket. Jacket has a finish time of 4, right? Okay, so jacket is finished first. So initially we have an empty linked list. So we are going to insert jacket into the front of the linked list. So jacket becomes the first node. Jacket becomes the first node of the graph. Sorry, of the linked list. Why it is so wide? So jacket is the first node in the graph. And then what is the next node to be inserted into the linked list?
Tie.
Yes, it's the tie, because its finish time is the second smallest. Then we have tie. And so we insert tie into the front of the linked list. So tie becomes the new head of the linked list. And then what else? What is the next node to be inserted?
The belt.
Yes, the belt. So let me write it over here. Jacket, tie, and then we have belt. Okay, so so after belt, should be shirt, right? And then we have, after shirt, what do we have?
The watch.
Yes, it's the watch. And then it is the shoes. And it's the pants, undershorts, and socks. Okay, so this is the output of the algorithm, which is just the linked list of the nodes. And let's say, okay, in the graph, we have an edge from undershorts to pants, right? So we're going to create the link to denote the edge in the graph with a purple color. Okay, so we have this one, and also we have an edge from undershorts to shoes. Undershorts to shoes. We have in the graph we have an edge from pants to shoes, and we have an edge from socks to shoes. Okay. So we have an edge from pants to belt. We have an edge from shirt to belt, and we have an edge from shirt to tie, from tie to jacket. Okay, and from belt to jacket. And then from tie to jacket. Okay, so here we basically represent the edges in the graph with the purple color. So here, can you say that for every node, for every edge in the graph, say in the graph we have an edge from socks to shoes, and then in the output of in the output, which is the ordering of the vertices, we say that socks appear before shoes, right? And then in the graph, okay, there is an edge from undershorts to shoes, and then in the total ordering of the nodes, undershorts appear before shoes. And also say, for example, if in the graph there is an edge from pants to belt, so we got a so then we can say that in the total ordering of the clothes, then pants appear before belt. Correct?
Yeah.
Yeah. So this means that the output respects this output is correct, because what we want to do is that if there is an edge in the graph, which starts from U to V, then in the output, U should be before V. So which respects this requirement. And this is the output of the topological sort algorithm. And let's look at it. Okay, so in the morning, if you wear your clothes by following this order: socks, underpants, pants, shoes, watch, shirt, belt, tie, and jacket. Does it make sense?
Yes, but I do have a question.
Sure.
Why would you put socks before the undershorts, for example?
Okay. Okay, so I mean, if yes, over here, so it's just so over here we got this result because when we call the depth first search algorithm, so the socks has a larger finishing time than undershorts. So which means that undershorts should be put before socks. But if you check the pseudocode of depth first search, which is over here, okay. So basically, we decide the order to visit these nodes. We visit all the nodes in this way. For each vertex in the graph, if its color is white, then we call the DFS visit function, right? So here, the reason why we got the socks before the undershorts is that socks has a larger finishing time than undershorts. But if we switch their order, if we switch the order of undershorts and socks, then we over here, if we switch their order, then so we could possibly get a situation where undershorts is weird. So we need to put on undershorts before socks. But even though in this way, it looks a little bit weird. So we put on socks before undershorts, but this is totally fine because you are not. So if you put on your socks first and then put on your undershorts second, there is no need for you to take off your socks before wearing your undershorts, correct?
Correct.
Yeah.
I think I
So
understood.
so this is also fine, even though it looks a little bit weird, but we don't get a situation where it says, okay, we should wear shoes. Let's say shoes, shirt, and then pants. We don't get into a situation like this, where shoes is wear before pants. So if the other person tell you, okay, you should wear your clothes in this order, you'll say, okay, it is going to give me trouble because before I put on my pants, I need to take off my shoes first.
Right, understood.
Okay, so this is what what the algorithm does. So it basically helps us to sort the nodes based on the relationship specified by the edges.
If I can also ask one more. So
Sure.
in terms of the watch is kind of like floating on its own.
Mhm.
Why would we put that after the shoes? Does that have
It's-
to do with the length list again?
Yes, it's totally fine because watch is an isolated node. So we put it on say after shoes yes, after shoes, just because we in the DFS in the DFS we visit we trigger the DFS visit function over the watch just right after the shoes. But this is like here you can just change the order. It doesn't matter. Still, it will give you a legitimate ordering of the nodes in the graph.
Okay, thank you. Understood.
Okay. So, any other question for me?
Wouldn't the runtime for this be long? Because you would have to compare, I guess, the value for each node.
Oh, not actually. Here we're not comparing the value of each node. Instead, what we got is this. Okay, so here they say here because you are talking about the running time, the execution time. So we need to focus more on the complexity. Previously, we said that when we talk about the complexity, so we need to focus on two parts of the algorithm, which is the function call and for loops, right?
Yeah.
So here we got a function call. So which is that we need to call the DFS. What is the complexity of DFS?
Isn't it n squared?
V plus E.
Oh yeah, yes. Okay.
And then, so as each vertex is finished, we need to insert it onto the front of the linked list. So basically, this is a for loop for each node in the graph. For each node in the graph, so we insert it into the linked list, right?
Mm-hmm.
So what is the insertion complexity of linked list?
Isn't it n?
No, it's O1.
O1. Okay.
O1.
Yeah.
Okay, and here we need to call the O1 complexity. We need to trigger the O1 complexity insertion function how many times? V times, right? So it will be V times 1, so it's still V. So the total complexity will be V plus E plus V, and still it is V plus E. So in terms of the execution time, it's not going to take long. So it's pretty more it's going to be pretty similar to the DFS or BFS function.
Okay, gotcha. Thank you.
Okay, sure. And this is the algorithm. So what I want you to know is that basically this algorithm can help us to sort the nodes based on the edges. The edge basically specify which nodes should go before the other one. So this is the output of these nodes. And can you think about any application of this topological sort algorithm in your life?
Maybe like taking classes for our major, like this prerequisite.
Yes, exactly. This is awesome. Okay, here, if we talk about classes, say here, you have different classes to take. Say 111. You need to finish 111 before 112. You need to finish 112 before taking 212 and 270. I need to finish 212 before taking some other classes like 345. 3 whatever. So basically, you can build a graph where the nodes represent the courses that you need to take, and the edges represent the prerequisite relationship. Okay, so then if you apply the topological sort over this graph, it will tell you, okay, by following which order should you take classes. Does it make sense?
Yeah.
Yeah. So previously, when I taught this course for the first year, I don't remember exactly. One student, even though I don't require anybody to do that, one student implemented the topological sort algorithm and created the graph by using the courses I think he's a CS major. He used that one. He constructed a graph by using that, and implemented the topological sort algorithm, and which gives the correct way to which gives the correct order of the classes that you need to take, and which is awesome. And what makes it even better is that that becomes one of his topics, one of his discussion topics during his job interviews with JP Morgan Chase. And he successfully found an internship at JP Morgan Chase, I think, or Goldman Sachs. I don't remember exactly, it's either JP Morgan or Goldman Sachs. Now he's a full-time employee over there. Okay, so this is the topological sort algorithm. Any question for me? Okay, if no, then I'm going to proceed to the strongly connected component algorithm. So the strongly connected component, algorithm, to learn that we need to know the definition of a strongly connected component. So basically, a strongly connected component of a graph is a subset of the nodes. For example, here we have a strongly connected component. The reason is because for every node in the strongly connected component, you can find a route from every node to any other node. So here in this strongly connected component, we can find a way to go from A to B, and also to go from B to A, right?
Right. Yeah.
Okay. So similarly, for here, for the pair of nodes, let's say B and E, you can find a way to go from B to E and also from E to B. There is a route for you to go from from E to B and B to E. Similarly, for this pair, A and E, you can go from E to A and also from A to E. So it's like a strongly connected component is basically a subset of nodes where for every pair of the nodes in the subset, you can find a route to go from either one to the other one. So and here we got another strongly connected component, so which includes two nodes, C and D. From C you can find the way to go to D, and from D you can find the way to go to C. Okay, now the question is that, is this a strongly connected component? Is this a strongly connected component, CDH?
Not really, because there's no place. No.
No, correct. So we can go from C to H, but can you find a way to go from H to C?
No.
No, there is no way for it to go from H to C, so this is not a strongly connected component. And here, previously we know that ABE is a strongly connected component, but here, let's say if this is a strongly connected component or not, if we can include F in that strongly connected component.
No.
No. So the reason is that we can find a way, just for example, we can find a way to go from A to F, but can you find a way to go from F to A?
No, you can't.
No, you can't. So we cannot include F in it. So basically, so the strongly connected component algorithm is going to help us to break the set of nodes in a graph into different subsets, where each subset is a strongly connected component. So here in this graph, we got 4 subsets or 4 strongly connected components, which are this. ABE is one strongly connected component. FG is another one. CD is another one, and H is another one. Okay, so we got 4 strongly connected components. So the output of the algorithm is basically different subsets or different all the strongly connected components of the graph. Can you think about any application of this algorithm? Where is it applied in your mind?
To be honest, not really too sure.
Okay, sure. I'm just going to give you one example. So for example, let's talk about a Twitter, okay? Because Twitter is, so here we have A, B, C, D, different people, different accounts on Twitter. And A is following B, and B is following, let's say, E, and E is following A, similar like that. And so, so the beauty of strongly connected component is that it basically can break all the nodes or all the accounts on this social network into different clusters, where the people in the same cluster cannot like share the same interest, because there is one way to go from A to E, and also there is one way to go from E to A. So this means that they share similar interest, and in this way, Twitter can just break their accounts or their users into different clusters or components, different components, where and then they can after they divide them into different components, they can analyze each component and find their interests. So then if Twitter gets some advertisement, say one gaming company is looking to to set up an ads campaign, advertisement campaign on Twitter, and then Twitter can use this component to find the component who is very interested in games, and then push those ads to those users to maximize their revenue. Make sense? Yes. So it basically it's basically a way for people to break the nodes inside a graph into different groups, where each group shares some similarity, has some kind of like similarity or common interest. So this is one very famous application of Twitter, and this is actually what most say social network companies do. They make money just by just through advertisement, and it's really costly. So they make a fortune from that. So for example, I'm not sure. So let's say, for example, if you install a game or any application on on the iOS store, or say on the Android App Store. On Android App Store, say for example, you install a game. So let's say one game. Can you give me one example of the game that you're playing, which is really very hot these days?
Call of Duty.
Call of Duty. Okay, I played that game in my college. It was the first generation of the first version, Call of Duty 1. Yeah, that's a very good game. So for example, if you purchase Call of Duty and you spend, let's say, $100 on the game, like let's say in the game you purchase something. I'm not sure what kind of things. Maybe you purchase a special gun, special weapon, or something like that. Do you know? Say if you spend $100 over this game, do you know how much money does this 100 go to either Apple or Google? Because this is Apple and this is Google. Do you know how much does it go?
Too much.
Can you say it again?
No, I just said too much.
It's 30%. 30% of your in-app purchases go to the platforms. That is written in the law. If these gaming companies do not pay this to the app, either Apple or Google, their application is going to be eliminated from the store. So that's how these two companies make so much money. I mean, this is a lot. So okay, and let's come back to the strongly connected components algorithm. So this algorithm is relatively easy. So first we call the depth first search algorithm over the graph. So and then we get the finishing time for each vertex, and then we compute GT. So what do you know what does GT stand for? What does the T stand for? It means transpose. Have you taken the 270 class or either linear algebra?
No.
Yeah,
Oh,
no.
okay. If you take those courses, any of either course, you'll be able to learn this. A transpose of the graph is like we keep the nodes in the graph the same, but instead it means that we are going to flip the directions of the edges. Flip all the edges. So for example, this is the original graph, and the transpose of the graph is here. So for example, originally this is the graph G. For example, originally we have an edge from A to B. Here we flip the direction of the edge from B to A. Previously we got an edge from B to E, and now we flip the edge from and make it from E to B. Make sense? Okay, so basically we just flip all the edges of the graph. And then we call the depth first search algorithm again over the transpose the graph, but in the main loop, we consider the vertex in the order of decreasing the finishing time, in which we computed from the first line. And then we just basically we're going to output the vertices of so this is the output. After that, we'll be able to see the output like this. ABE is one strongly connected component. CD is another one. FG is another one, and H is another one. So here you can see that we can get the we can calculate we can discover the strongly connected component of the graph by using two calls of the depth first search. One call over here and one call over here. So guess what is the complexity of the strongly connected component algorithm?
V plus E?
Yes, it's the same, V plus E. The reason is that here, the first function call is the complexity is V plus E. The second one is that we need to flip all the edges. So the complexity is E, the number of edges. In the third call, we have V plus E complexity. So if we sum them up, it will be 2 times V plus 3 times E. So here, if we talk about complexity, we should ignore all the constants and only keep the dominant part. That's why we got the V plus E complexity.
How do you flip an edge?
Mhm.
How do you flip like the edges, and how would you do that?
Just change the direction. So previously, if we use here, you can see that we have an edge from, originally we have an edge from A to B, but here we flip it from B to A. And here, if we use the GCC matrix representation, so this is the matrix for the original graph, because we have an edge from A to B. Let's say this is row is for A, B, C, D. A, B, C, D represents the nodes. Okay. In the graph G, we have the edge from A to B. Correct.
Yeah.
So we need to mark this place 1, but we don't have an edge from here. We don't have an edge from B to A. So we need to mark this place 0. Correct. And then in the flip, the representation of the adjacency matrix representation, we keep the nodes the same, A, B, C, D, A, B, C, D, but we just change the it. Okay, so here we change this from originally it is 1. Now we change it to 0. Originally it is 0. We change it to 1. So basically, you just flip you just change all the 1s to 0 and all the 0s to 1.
Okay. All right.
Make sense?
Yeah, it does.
Okay. So this is the strongly connected component algorithm. So here, for these two algorithms, you just need to understand what is the input and what is the output, and know that both of them rely on depth-first search. That's my requirement for you. Okay. So and also today, I think a relatively more important thing is here. It's something that I want to discuss with you. So, can you see my screen?
Yeah, we can see it.
Okay. So okay, yes. Can you see the coding task?
Yes, we can.
Okay. So I got this question when I did one of my first code interviews. So I think it was in the year 2013 when I first applied for internships. And I didn't, as I told you before, I didn't expect it to be so technical. But so after I applied through their website, this company is called Misfit. So at that time they were a company that is focusing on smart watches like the Apple Watch now, which can monitor your health, and so which can monitor your health condition. I'm not sure if this company still exists, but at that time it was it was just a small company with like 20-30 employees, and it's based in California. So I applied through their website, and then one day their HR contacted me and asking this. They asked me to spare this amount of hours in the email. They asked me to do this, spare at this 0.06 hours for the interview. I was like, do they miss a point over here? Do they miss so I thought it should be something like 0.6, and so I sent them an email again, and they told me, okay, it's not 0.6. It means 6 hours. After realizing that it's 6 hours, I was like, holy! So this should be something very heavy. And then so I scheduled a time with them, and then at the beginning of the job interview, they just sent me this document, okay, and asked me to send my code back to them within 6 hours. And I have to return all the code in C++. So, and actually here you can say they give me 3 questions. The first one, the second one, and then the third one. And to be honest with you, after reading the first 2, I was like, what are they asking me to do? I couldn't even understand the question in the first 20 minutes. I don't even understand these 2 questions. So I was hopeless. And then I just say, okay, I'm going to check what is the third one. And I found, okay, this is, even though this is the last one, but actually this is the easiest one. This is the easiest one. So, and then I start doing this one, and it kind of like give me some confidence. So here I just want you to go through this question and then try to understand it, and also think about what kind of solutions can you come up with. Okay, I'm just going to give you 5 minutes to read this question and let me know if you can understand it.
Professor, where is S?
Sorry,
Where is S?
where's F?
S.
X here. You can see in the graph.
The,
in the,
the
in
S
the
as in Stephen.
Oh, S is Steve here.
Okay, thank you.
So tell me, Zaf. So is there anyone who understands this question?
Yeah, so like the first thing I think we have to do is like figure out what we're going to use, like for like data structures.
Mhm.
Like algorithms.
What
I
kind
think
of
we have
data
to-
structure do you think that we need to use?
So we need like a linked list, and we need BFS, right? Breadth first search.
Yes, we need BFS, but not linked list. We need graph because you are using BFS over graph, not a linked list, right?
Aren't we returning the values as a linked list though?
Okay, you want to return the value in a linked list. Okay, yes, it's fine. Yes, cool.
So you could
Okay,
just like add, like every point you visit, you could add it to the linked list.
Yeah, okay, cool. Yeah, I got you. Great. So yes, you got it correct. Okay, so this is a question. Basically, what this question asks us to do is that okay, so it give the input is and the static length of the map, and the m is the number of random barriers. So and then so x1 y1 is the coordinate of the start, x2 y2 is the coordinate of the of t of the destination. So here basically so it will generate a n by n grid or matrix like this, and where some random number of m barriers like the x is going to be randomly placed over the cells of the matrix, and your task is to find the shortest path from S to T. Okay, and then so also it says, okay, given the set length of the map, the time complexity of your program should be equal or below O squared. Okay, so it's, I mean, I'm pretty glad that you related it to BFS. Yes, we can definitely, this is the correct answer. We're going to use BFS to solve it. What is the complexity of BFS?
It's O of V plus E.
Yes, OV plus E. So if we build a graph, for this matrix, whose size is n by n, how many nodes are there?
That is n squared.
Yes, the number of nodes is just n squared. Cool, because each cell is basically a node. And how many edges are there?
I think just n.
No, more than that. The edge, so here you can say that, let's just pick a random node. So let's check this node. Let's just check this node. How many nodes is it connected with?
Is it 8? You could go to like 8 different sides.
No, it's not 8, it's 4. This is because as what we find in the graph, it says that every step you can either move left or right or up or down. So it means that if you are at this node, if you are currently at this node, then you can go, I'm going to use a different color. Okay, so you can either go up. So this is.
Also, you can't go like diagonal.
Yes, you can go either go up, go left, or go bottom, or go right. So at each node, you can visit. Each node can have at most 4 neighbors. So the total number of edges is basically at most 4 times the number of nodes. And since less than or equal to 4, so then this is also going to be at most 4 times n squared. Correct? So if we use the BFS to solve this problem, then the time complexity would be n squared at most, n squared plus 4n squared. 4 times n squared. So 5n squared is also n squared. So if we use BFS, then it satisfies the complexity requirement. Okay, cool. And how do we solve this problem? Basically, for each node, for each cell, you can just model it as a node. and then say if it can, if it can go up, then you basically build an edge from this node to the node above it, and for the node to the left of it, if to the node to the right of it, and to the node to its bottom. But if there is an X, meaning that this place is not unreachable, is not reachable, so then you should break that edge. There is no edge in that direction. Do you know what I mean?
Yeah.
Okay, so this is how you build a graph. After you build the graph, you can specify the source node. We definitely know the source node because BFS takes the input, which is a graph, undirected graph, plus a source node. So we, based on the coordinate of the source node, we know so which node, based on the coordinate of a source, we know which node is the source node. Okay, so that is the input that you pass into your breadth first search algorithm, which is the graph that you build, and also the source node. And then what is the output of BFS?
The shortest distance from like I guess each node.
Yes, from the source to every other node, to all the other nodes. And then after you search, you find the shortest distance from the source node to every other node. You just need to, based on the coordinate of the destination, you can find the shortest distance from source to destination. Correct? Correct?
Yeah, correct.
Yes. So I mean, so like if you read, after you spend 5 minutes reading this, so just type in 1 in the chat area if after reading the question you understand the question and you relate it to BFS. Just type in 1. Not based on my explanation, just before I explained. Okay, cool, wonderful. I see 3 ones. That's wonderful. Okay, so this is the ability that you must need to have. Okay, as I said, among the 3 questions, this is the easiest one. So so I mean, if among in the 6 hours you have, since you have 6 hours for this interview, you can spare at most 90 minutes or say 80 minutes for this question at most. And what makes it more difficult is that they ask me to implement it in C++, and you know the coding load of C++ is way more than Java. So let me show it to you. Q3. This is my solution to Q3. Okay, so here you can say that in total I wrote this. I wrote these files, the CPP files and .h files. So here, so first I defined a class for node. So each node has a set of so here I use this to denote what are the neighbors of this node, and each node has this information: the coordinate, its color. So because its color, remember, its color is either black or white or gray. Say here I defined the colors white as 0, gray as 1, black as 2. The same as what I did for you in your scheduling code for your homework 8. And then the size of the matrix and the distance to the source. This is D, and this is the parent. Is pi, the parent. Okay. So and then this is the implementation of the node. Okay. So a couple of functions like the constructor, and then so how to find the neighbors of this node. Okay, and then so these are the two files that I implemented, and then this is the map. So which is kind of like the graph that I built. So the map has the breadth first search algorithm, and find the shortest path function. And this is the definition of it. And here you can see that this is exactly the BFS search algorithm. And then this displays the shortest path from the source to the destination. And then here is the input, the constructor, which is like the size, the side length of the matrix, the number of barriers x1, y1, x1, y1, and x2, y2 are the coordinates of the source and destination. And here I also implement the function to generate random barriers. So you can say I use the default random engine as the random number generator. Okay, so and then finally it's a main function that does the test that I use for the test. So and then and after here is the result after you implement that. So it says, okay, the shortest path from the source coordinate to the destination coordinate is this. Guess how much time did I spend on it?
A whole day.
Hours.
You can't spend a whole day because they only give me let's say around say 6 hours in total, and I think I spent around 80 minutes, 1 hour and 20 minutes in total for this. And the total number of lines of source code that I wrote is 56 plus 187. It's like 243 lines. And also the debug. Okay, so and then I just spent the rest of the time focus spend most of the time on the other two questions, and I got two. Among the three questions, I successfully solved two, and I got another one, let's say 60 or 70% resolved because I'm running out of time. So I couldn't finish that one, but I know how to finish that. Don't know what is the end of that interview. What is the end of that story? Did I get it?
No.
No. Yes, even though I think I did an okay job, but still I didn't get it. So, which is pretty harsh, but I really appreciate that experience because it lets me know what is the real world job interview like. So in the future, I prepare a lot for that. So, and this is what you are going to experience when you are going to the job market. So be prepared. That's why I keep teaching you, okay, what is the complexity of an algorithm? And so I use examples to explain the algorithms. Okay, so this is the ability that you need to have when you are at the time when you are on the job market. Okay, so that's any question for me before we go?
No, I'm okay.
Okay, and then that's the end of our lecture today. So have a good week.
Thank you.
Thank you.
Thank you, Professor.
Thank you, Professor.